All right, guys, we are going to start chapter 14. We're talking about waves and sound. So you may think you know quite a bit about sound and about sound waves. One thing you should realize is that sound waves are not the same thing as light waves. That seems like you would know that already, but just keep in mind that light waves come in electromagnetic waves. We will talk about that in the next chapter. Sound waves are something completely different, and they behave very differently as well. So to get this down, you're going to need to know the parts of the waves and how to describe them and how they relate to one another. So when I'm talking about a wave, the first thing you should think of, probably what you think of, is like the waves in an ocean. All right, so you've got your high point, which would be your crest, and you're going to have your low point, which would be your trough. Now, if you're measuring the distance from crest to crest or trough to trough, that is going to be your wavelength, how far it is in between them. Your amplitude is going to be how high the waves are, and your frequency is how many pass a certain point every second. So if you're sitting in the wave pool at Fiesta, Texas, and you're standing there and you're not moving, however many times the waves hit you every second, that's going to be the frequency of the waves. And frequency of the waves are going to be related to wavelength, which is how far apart the waves are. So if the wavelength is very small, if your crests are coming really close together, then they're going to hit you more often than if the wavelength is long, because it's far away from crest to crest, your frequency would be really low. So we would say that wavelength and frequency are inversely proportional. So if one gets bigger, the other gets smaller. So if you have a big frequency, a big wavelength, they're far apart, then the frequency is very small. And if you have, so if that's a short wavelength, you're going to have a high frequency, and a long wavelength is going to be a low frequency. Now, I don't really remember them when I'm doing them as an inversely proportional. I just remember that long goes with low, and they both start with an L, so that's how I remember them. So this would be the formula for it, where F is frequency, the V is going to be the velocity, and the little lambda sign that's there underneath the V, that is called, that's the symbol for wavelength. And so I can always remember that lambda is a symbol for wavelength because it's got that little wave at the top, that little, it's like I picture this as a little character, and he's got a big wavy hair thing going on at the top of his head. So that's lambda, that means wavelength, frequency, and velocity. So as you increase your frequency, then you're going to decrease your wavelength. That means it's shorter in between waves. Your crests are coming closer and closer together. So our velocity is going to be our speed, and it's always going to be in meters per second. And that is because the speed of something is going to be affected by its wavelength and its frequency as well. Now, wavelength is going to be in meters, and our frequency are going to be in hertz. That's not hertz like it hurts to do something, but hertz as in the guy's name who came up with it. So there's a couple different types of waves. You've got transverse waves, which picture those as being like a jump rope. If you were shaking a jump rope up and down, or when we were talking about the waves crashing onto the shore at the ocean, those are going to be transverse. Propagation, which is how they travel horizontally, but they oscillate up and down, so it's going to be vertically. So the propagation and the oscillation are perpendicular to one another. So this would be an example of a transverse wave where you've got your crest here at the top, you've got your trough down here at the bottom, and a crest here at the top. Wavelength is going to be from crest to crest. Its direction, if we're saying that this is the start and this is the finish, if it's a jump rope and you've got the guy standing here holding this end of it, and this side is attached to the table, that would be really big jumps there, but its propagation, the way it travels, the wave is traveling in this direction. Its oscillation, which would be its movement, is going to be up and down. So if you were to tie a ribbon right here, this ribbon would go up and down, up and down, up and down, while the wave moves this way, right? So propagation is how it travels. Oscillation is how it moves up and down. All right, so the next type is called longitudinal. I want you to think of that as kind of like a slinky, how a slinky would move. So in this case, longitudinal, the propagation is going to be horizontal and the oscillation is also horizontal. So if you've got a slinky, and it's not a great picture, but they don't really have crests and troughs. Instead, they have the places where they're compressed, and they have the places where they're spread apart, which is called the rarefaction. And so your wavelength is going to be between compressions or between rarefactions. And so what happens is rather than it moving up and down, up and down, up and down, the slinky is actually the motion, the oscillation is back and forth right here, and the propagation is only going to be that way. So they're going the same direction. So transverse, your movement is going up and down while your propagation is horizontal. And longitudinal, propagation and oscillation are both horizontal. Click on the link and complete the homework, and I'll see you in class.